Hello friends, welcome to Notebook videos on measures of central tendency. This is the most important segment in statistics that you need to learn before we proceed onto more difficult concepts. The measures of central tendency are the most fundamental concepts in statistics and most commonly applied in real life. You may already be aware of these concepts, the mean, median, and mode. When you are looking at a distribution such as this, you will have different points for the mean, median, and mode. Whereas in a perfectly shaped normal distribution, the 3 points would coincide. Here we see the variations in the mean, median, and mode values given a left skew, right skew, and normally shaped distribution. So what do these values exactly represent to be on different points on the distribution? So, what do these values exactly represent as they are on the different points of the distribution? Well, if you carefully notice, with all the distributions, the mode is at the highest point of the curves, indicating the highest frequency. The median is meant to typically divide the values in the curve in exactly 2 halves. So, it will be at the point where the area under the curves are exactly the same on either sides. Mean would instead indicate the point of value of the average data in the curve. The mean is also called the arithmetic mean of data. It's expressed as the total of all values in a particular data set divided by the total number of observations. So mean, x bar is equal to x1 plus x2 plus x3 plus xn by n. An important point that needs to be noted here is that the data set may contain negative values. So do not get confused on how to add if there are negative numbers. Numbers would have to be added with their signs. Here we see the example of negative integers in the data set, and so the mean would be the summation of all the values along with their signs, which is 6.4. A data set that has a set of data and one unknown data can be solved for if the mean is known for the data. So let's say we have 12, 5, 7, minus 8, 10 and x, the unknown observation. And the mean for the data is 5. The problem is solvable by simply putting the numbers together and solving for the value of x. Point to be noted here is that the data is ungrouped data. In case of ungrouped data, we express the arithmetic mean as a summation of all the observations divided by the total number of observations in the data. There's also other methods to find out the arithmetic mean for such kind of data. For example, let's look at this data set. Here we have scores or marks listed for a bunch of students. In this case, we somewhat assume that the mean of the data is at 80 and try to find the true arithmetic mean. Remember, 80 is a safe assumption given it's fairly there at the midpoint of the table. The process of trying to find the arithmetic mean is also called the assumed mean method. So, with the assumed mean, which is 80, given by capital A, we can calculate the deviations of the observation, here x, from the assumed mean. Deviations can be written as d. Thus, d is equal to x minus a. Values can be simply tabulated in another column. The frequency column is then tabulated as fd as the last column, where frequency is multiplied to the d's or deviations in the assumed mean method. So, you're basically trying to understand by how much the frequency values are dividing from the assumed mean. The assumed mean method calculates the arithmetic mean as the sum of assumed mean 80 added to the summation of all the values in the last FD column, 115 here, divided by n, which is the total number of observations, 50. So, if final arithmetic mean is equal to 80 plus 115 by 50, and that's about 82.3. Notice that 82.3 is not far from the assumed mean 80. It's important to remember the formula as just shown, with the frequencies multiplied by the deviations and then divided by n. This is then added to the assumed mean. The next most celebrated tool in statistics is the step deviation method. It's a bit of a refined assumed method that is adopted if x minus a values, or in other words, values turn out to be very big. In such cases, the d's are divided by a common constant, say c, to reduce the product values of frequency multiplied by d. Finally, of course, this adjustment would have to be compensated by multiplying the same value again to the formula of am, which is summation of f times d divided by nc, and then finally multiplying by c. Well, my friends, I think we have delved enough into the concepts of arithmetic mean. Now, we have to simply compare the methods we just learned for a better understanding. Three main methods have been harped on: the direct method, the assumed mean method, and the step deviation method. And let's look at a quick example here for grouped data. Here we have the direct method, where the first two columns are obviously given, the frequencies corresponding of each of the classes. Xi is the class mark for each of these class intervals. Thus, the third column that needs to be written in case of grouped data with class marks. If data is not grouped, you will have single x values in the first column, and those can be directly multiplied by the frequency values in the second column. Finally, the fourth column is the xi times frequency column. That is, product of class marks and frequencies. When data is calculated, the third and the fourth column, we get the final sum values of all values, product of frequency and x values. So, by the direct method, the am is given by summation fi xi divided by summation fi. That is, sigma fi xi by fi gives the x bar or mean value. Thus, by the direct method. By the assumed mean method, everything is same up till the fi and xi column. It's only the last two columns that would change again. And here we calculate the di instead of the fi xi. Di is given by xi minus a, where a is assumed mean. So, if we have assumed mean of 32.5, then di values would have to calculate it by the value of the observation minus a for each row. So, the third column would have some positive and negative values. The fourth column would simply be product of the fi and di values. Here we calculate the mean value by the assumed method again. It's important to note that here it's the same value as that found by the direct method. Remember that the chosen a can be any value from the column of the class marks and doesn't have to be 32.5. With any chosen value, you will get the same result. Finally, we have the step deviation method. And in that, we need to include one extra step where the di's get divided by a constant c, which is usually the width of a class interval. In this case, therefore, we considered c to be 15. And let's change the a here and consider it to be 62.5 instead of 32.5. The fourth column is nothing but the product of the frequency values and the ui's. So, my friends, we come to the end of the first part of measures of central tendency. I hope you're now well versed with the three ways by which the measures of central tendency can be calculated. In our next video, we shall discuss the mode and the median topics. Till then, goodbye.